answered correctly is 4.9 with a standard deviation of this. Interpret the results. The expected number is 4.9 with a standard deviation of 2. Okay. The expected number of questions answered correctly is 4.9 with a standard deviation of 2. Yes, but I want to read the other two. The expected number of questions answered correctly, no. The expected number of questions answered correctly is 4 with a standard deviation of 2. Oh, no, it's just, yeah. Good. Other questions? Did we answer your doubts or your question or not?
Yeah, thank you.
Thank you. Other questions from anything?
No, that was really helpful. Thank you.
Thank you. Anything else? Or we continue and try to finish up 6.2 then?
I think I'm ready to move on to 6.2.
Okay, me too. Good. Anything else?
Yeah, I found 6.1 and 6.2 like really difficult. If we could go over another question in 6.1, that.
Of course, yes. Anyone?
I can't remember which question it is. I know it was this one, and I think it was maybe 15. I think my layout is slightly different than yours.
Let's look at 15. It was this one?
No, it was one of those other problems like you had to work.
This one?
Yeah, that one gave me trouble too.
Okay, let's take a look. Is this a good one then?
Yes.
The following data represent the number of games played in each series of an annual tournament from 1923 to 2003. Complete parts A through D below. Okay. Construct a discrete probability distribution for the random value by x. So let me copy the table. So this is what problem? This is problem 13 and 6.1. So x and p of x, and we have 4 and 5 and 6 and 7. And the frequency is 15, 14, 22, and 29. Perfect. So first we want to construct the probability distribution. Okay. So we always have to look at the total for the frequencies. They may have told us or not. We don't care. We still should calculate this just to make sure. 22 plus 29. So the total is 80. So in order to determine the probability for each outcome for x equal 4, the outcome for the probability for x being 5, x being 6, x being 7, first of all, I have to remember to always check they have to add up to 1. If they are 0.99 or 1.01, something is wrong. I have to go back and adjust. Okay, so I will divide 15 by 80 and put the number here. 14 divided by 80, put the number here. 20, these are the probabilities. So the probability for x to be 4 is frequency 15 divided by 80. The probability for x to be 5, the number of times we get 5 is 14 divided by 80, and so on and so forth for the other two. So 15 divided by 80, and then 14 divided by 80, and then 22 divided by 80, and finally 29 divided by 80. So I'm going to round up to 0.19, 0.18, but they may, let's see what they want, because they may want all 3 decimals. Round to 4. Oh, okay, then I can't round at all, which is fine. Okay, so 1.875, 0.175, 0.275, and 0.3625. I have no doubt that they add up to 1. unless you want to check. There is no way, unless I copied something incorrectly. Otherwise, they have to add up to 1. There is no rounding of any kind. So 0.1875, 175, 275, 3625. Okay, perfect. So I'm going to enter those values. So 0.1875, then 0.175, then 0.275, and the last one, 0.3625. Graph the discrete probability distribution. Again, I don't like just selecting something. I like to present my own work. And you have to do this on paper anyway. So, okay. So this is 4, 5, 6, and 7. The highest probability is 0.36. So 0.1, 0.2, 0.3, 0.4. So this is the probability, and this is x. So for 4, I have 0.2 and 0.3. 0.4 is a little bit under 0.2, so right here. For 5 is under a little bit lower. For 6 is close to 3. And for 7, close to 4 actually. So that's the probability distribution, the histogram. Okay, so let's take a look now. Okay, so small, smaller, high, high. But I have to be careful because these two look very similar. So 1, 2, 3, 4, 5. 1, 2, 3. No, this cannot be it. Because 7 has to be at 3.6. So these are completely off. And by comparison, these kind of look similar, but the numbers are incorrect. Okay, computer interpret the mean of the random variable x. Okay, so we either put in the calculator or determine with StatCrunch. So what would you like me to do?
I had a really hard time trying to use StatCrunch.
Oh yeah, this is a very simple, it's just a double click here, really. So you go to top with the stats, calculators, and you use the bottom, custom. And this is your x, and this is your frequency, or also called weights, and just compute. So the mean is, so mu x is 5.825, and the standard deviation for x is 1.1190817. So back to the problem. Round to 4 decimal places. I will have exactly everything. So 5.8125. And then check. And if played many times, would be expected to last about no. If series, if played many times, would be expected to last about 5.8 games. Computer standard deviation, we already have it. How many 1 decimal place? I will write 1.1 then. Okay, any questions? Is this better now? We feel better?
Yep, I'm good. Thank you.
Yes, thank you so much.
My pleasure. Anytime. Please always bring to class any question, any problem, because as you know, there is no time for me to do everything. It's not possible. So thank you so much for doing that. Okay, so now let's finally talk about a last section, which is 6.2. So here we have an example of a discrete distribution. It's binomial. Binomial, also random variable, or experiment. We use them interchangeably. If we talk about the random variable, that is binomial. We can also talk about an experiment that is binomial. Same thing, pretty much. Okay. So we know what a discrete random variable is, what we just had. X to be 4, not 4.11, not 5.99. So these are this is a discrete random variable. Same thing here. But we classify a random variable to be binomial if it fulfills 4 conditions. If it does not comply with these 4 conditions, it's not binomial. It's just discrete, but not binomial, or maybe some other type of discrete random variable, but not binomial. So here are the 4 conditions. Number 1, we have to have a fixed number of trials. So this is just denoted by n. What do I mean by number of trials? Number of people. Number of times I repeat the experiment, right? So fixed number of trials, n. Part B, or the second condition, trials are independent. If they're not independent, then if any of these conditions fails, it's not a binomial random variable. Part C, or this third one, there are only 2 mutually exclusive outcomes. We like to call them success and failure. You don't have to call them like that, but we like to call them success and failure. And the last one, the probability of success is always the same. From trial to trial is denoted by P. The probability for a failure is denoted by Q, which is 1 minus P, as we know. It's the complement. So if all these conditions are fulfilled, we say it's binomial. Also, how do I determine the mean and the standard deviation for a binomial? So these formulas are for binomial. Random variable only. 2 very simple formulas. It cannot be easier. NP, N, the number of trials in the experiment, and P, the probability of success. This one is the square root of the same thing multiplied by Q. Here's a formula that you do not have to memorize. I'm not going to ask you to use it unless you want to use it. So if I know that X is a random variable that is binomial, and I want to determine, let's say, the probability for X to be 3, then there is the formula that says, let's say N is 10. And the formula would be N, let me write exactly the numbers. 10, choose 3. The probability, let's also say that the probability is 0.2. 0.2 raised to power 3 times the rest, which is 0.8, the Q, PQ, to 10 minus 3, which is 7. So in general, here's the formula. P for X, so this is N choose X, P to X, 1 minus P to N minus X. We're not going to use it. I'm not going to force you to use it. We're going to calculate everything with a calculator or StatCrunch. Now, one remark, and then we can start working on problems and see where this is applicable. One remark or note that I want to add here is as n increases, then the probability distribution of the binomial random variable will get closer and closer to or becomes bell-shaped. Important note. Okay? So in general, we say that n times p times 1 minus p has to be greater than or equal to 10 for this to happen. N number of trials, probability of success, probability of failure, 1 minus p, has to be, if this product is greater than or equal to 10, that's almost certain that the distribution, the binomial distribution, is almost bell-shaped. Okay. So now let me share my screen and let's go to, where are we here? Here. Now let's work on 6.2. Anything you want to start with?
Numbers 11.
Number 11. Perfect. Okay. The binomial probability experiment is conducted with the given parameters. I'm going to write them down. So n is 9. That's the number of trials. P, the probability of success, is 0.3. Right away, I will write the Q is 0.7. And they want us to find x less than or equal to 3. The probability of x less than or equal to 3 successes is blah, blah, blah. I don't care. Let's talk about it. So we have n equals 9, right? And in 9, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The probability for each a trial is this, for each success is this, for failure is this. The question here is asking us to find the probability that x is less than or equal to 3. Well, what are the possibilities for x? 0, 1, 2, according to this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the probability for x less than or equal to 3? Is this. Meaning the probability for x to be 0 plus the probability for x to be 1 plus the probability for x to be 2 plus the probability for x to be 3. And we'll calculate this in a minute. What if I'm asked to find the probability for x equals 5? Then there is only one probability. Just x equals 5. We're going to calculate all of these. Now, what is the probability for x to be greater than 6? So the probability for x to be greater, strictly greater, not equal to, is this. The probability for x to be 7 plus the probability for x to be 8 plus the probability for x to be 9. There is nothing else. And yes, we're going to calculate these, but how are we going to calculate them? We're going to calculate them. There are many options, but I'm going to show you both with the calculator as well. So in order to determine this, there is something in the calculator that helps us calculate this. If I calculate this and subtract from 1, then I get this probability of 7 plus 8 plus 9. So that is 1 minus binomial probability P, no, cumulative, sorry. CDF, not PDF. I'll explain PDF in a moment. But no, we only need CDF right now. When we cumulate, it's a cumulative. So probably CDF, I'll show it in a moment. With N, P, X. What is N? 9. What is P? 0.3. And what is X? 6. Because that's what I want to calculate. The binomial cumulative density function, CDF, cumulative, will add this plus this plus this plus this plus this plus this till it stops at 6, including 6. So from the entire sample space, which has probability 1, I subtract these to determine this probability of 7 plus 8 plus 9. You can say, I don't want to do that. Fine. So you're going to get the same answer if you just determine with the PDF. Binomial PDF for 7 plus for 8 plus for 9. So we're going to do it in 2 ways so you see the difference. This is so much easier because I don't have to repeat it 3 times. So what is the syntax here? Is NPX, the same thing. NPX. So N will be 9, P will be 0.3, X will be 7, and then plus. The same thing with 8, plus the same thing with 9. But we're going to get the same answer, and this is so much faster. So let me stop. Let me share my screen.